Hello my dear students, welcome to EPG Pathshala. I am Anshul Srivastava from Department of Physics, Institute of Science, Banaras Hindu University. Today we are going to talk on the module titled Nanofibers Electrospinning Technique under the paper Nanoscience and Technology 2. After completing this module, my dear student, you are able to learn the one-dimensional nanofiber or quantum wire, electrospinning technique in detail, electrospinning technique for growth of polymer nanofibers. You will also able to know controlling the various parameters in electrospinning setup for optimizing growth of one-dimensional polymer nanofibers. One-dimensional nanostructure, wire, rod, tube, fiber, belt are for current interest due to their wide range of applications in mesoscopic physics and nanoscale devices. In contrast to the other nanostructure, one-dimensional nanostructure can provide unique advantages for the investigation of the electrical, mechanical and thermal dependence performance on dimensionality. For the potential application of one-dimensional nanostructure into existing microscopic devices, there is a great need to develop a novel synthesis route for one-dimensional nanostructure with nanoscaled diameter and macroscopic length. Since 1990s, electrospinning firstly patented by J.F.K. Gule in 1900. Gule JF patent GB 06385 titled Improved Method of and Apparatus for Electrically Separating the Relatively Volatile Liquid Component from the Components of Relatively Mixed Substances of Composite Fluid on 19th May 1900, which is a novel, simple and facile technique has been attracted numerous scientists' attention for the growth of one-dimensional nanostructure having continuous length, tunable diameter, aligned direction, diverse and controllable compositions. During the electrospinning process, electric field force act on the polymer solution or melt to form the electrospun jet. Finally, solidified fibers can be achieved by stretching the electrified jet for the electrostatic repulsion between the surface charge and the evaporation of solvents. Till date, electrospinning field has been evaluated as the fast-moving front in material science. Therefore, in coming slide, I am going to elaborate electrospinning technique. I want to discuss electrospinning setup. From 1990s, a number of advanced technique has been developed for the generation of one-dimensional nanostructure, including electron beam or focused ion beam writing, lithography, hydrothermal chemical vapor deposition, electrospinning, solution method, etc. Among these methods, Electrospinning is the simplest method to fabricate one-dimensional nanostructure with both solid and hollow interiors with continuous length, tunable diameter, aligned direction, diverse and controllable composition. Different from other method for growth of one-dimensional nanostructure, electrospinning is based on the electric field force acting on the polymer solution or melt, which can be regarded as a variant of electrospray process. In electrospinning, solidified fiber can be achieved by stretching the electrified jet for the electrostatic repulsions between the surface charges and the evaporations of solvent, which is shown in the figure. This technique could be applied to synthetic natural polymers, polymer alloys, and polymer decorated with functional nanomaterials. These unique advantages of electrospinning afford the multifunctional properties for diverse applications. Electrospinning setup has clearly shown in the figure. This setup contains three major components. The first component is the syringe pump with a metallic or plastic syringe. The second, high voltage DC or AC power supply, and the third one is fixed collector plate or rotating cylinder. In the setup, syringe is used to inject the polymer solution at controlled rate with the help of syringe pump. As the high voltage is applied through high power AC or DC power supply, the drop of polymer solution at the tip of syringe is polarized and the induced charges are distributed over the surface. Under the influence of a strong electrostatic field, the charged polymer is accelerated towards the collector. The role of electrostatic force here is to supplement or replace the conventional mechanical forces, for example hydrostatic or pneumatic, used to form the jet and to reduce the size of the fiber. Hence, he known as electrohydrodynamic jetting. Here, collector plate should be of good electrical conductivity to neutralize the charge carried out by the polymer nanofiber. The process of electrospinning. I want to discuss some basic process which occurs in electrospinning. Before moving further, one can raise questions like why electrospinning nanofibers? Fibers can be made much thinner through electrospinning than other methods. Now, how the electrospun fiber are thinner down in electrospinning? A solution of liquid polymer fluid is put through a capillary device to produce a droplet. Next, a voltage is applied to the droplet which reduce the surface tension, resulting in very thin fiber being drawn out. The voltage applied is very high. Typical value range from 8 to 25 kilovolt. The diameter of the fiber is inversely proportional to the applied voltage. The fiber is then drawn towards a collection plate by gravitational and electrostatic forces. The fiber become randomly arranged on the collector plate, forming a mesh network. Now, I want to discuss some of the basic theory of electrospinning, such as the theory of electrospinning could be divided into few categories. The first one, the theory on the fluid charging. Theories on the liquid droplet under the high voltage, that is called Taylor-Cone theory, and the theories on the jet in flight instability theories, where liquid droplet under high voltage, it is called Taylor-Cone theory. The second one is the liquid drop under high voltage, which can also be called as Taylor-Cone theory. In 1964, Sir Geoffrey Ingram Taylor established the Taylor-Cone theory to describe the deformation of a small volume liquid under the high electric field. As a small volume of electrically conductive liquid is exposed to an electric field, a stable shape can be acquired owing to the equilibrium of the electric forces and the surface tension in the case of Newtonian and viscoelastic liquid. As the voltage is increased to a critical potential, and any further increase in potential will destroy the equilibrium. Thus, the liquid body acquires a conical shape with half angle of 49.3 degree, a whole angle of 98.6 degree, referred as Taylor cone, which is shown in figure. Additionally, Taylor also demonstrated that the shape of such a cone approached the theoretical shape just before jet formation within the electrospinning process. Taylor derivation is based on two assumptions. The assumption number first, that the surface of the cone is an equipotential surface, and the second, the cone exists in steady state equilibrium. The formula UC square, where UC is the voltage, is equal to 4h square by L square, where h is the distance between the tip and the syringe and the collector, L is the length of syringe, in bracket ln 2L by R minus 3 by 2 bracket closed 0.117 pi gamma R, where R is the diameter of tip of the syringe, gamma is the surface tension of the solution. Jet in flight, which is thinning. Here I want to discuss the jet formed during the electrospinning and instability theory. It has been observed that during electrospinning, the charged jet injected from the Taylor cone passed by in a nearly straight line, proceeded by bending into a complex path, during which electrical forces stretched and thinned them by large ratios. Schematic illustration of the jet path between the tip of syringe and collector has been shown in the figure. As the fluid is injected from the cone, the continuous thinning of liquid jet can be observed. The charged jet will accelerate in the presence of electric field created by the countered positive and negative potential as shown in the figure, and this plate is kept at ground potential. Several attempts has been made to explain such trends in electrospun jet operation as function of fluid and operating parameters under experimental control. Within certain limit, for a given fluid, there exists range of driving voltage V and flow rate over which the electrospinning can be maintained stably for longer period. The electrospinning process continued an electrical circuit so one can measure as well the current flowing through this circuit. The characteristic length over which the initial dramatic thinning of jet takes place can be identified with the axial distance where advection and conduction current are equal. Following relation is of this nozzle regime length L, L to the power 5 equal to K to the power 4, Q to the power 7, rho to the power 3, Lx chi whole square, by 8 pi square Ex p z square, where K, Q, small q, V, E, I and E are conductivity, flow rate, density, aspect ratio, applied field, electrical current and dielectric constant of outer fluid. Typically, air is the conventional electrospinning. Beyond this characteristic length, the jet thins more slowly, sufficiently far from nozzle. The jet approaches the asymptotic regime where all the terms except electrostatic and inertial must eventually die out. Here, I want to discuss the several parameters which one need to care during electrospinning, which needs for a good quality growth of nanofiber. For the growth, working parameters are very important and one need to understand not only the nature of electrospinning but also the conversion of polymer solution into nanofibers through electrospinning. These parameters can be broadly divided into three parts such as solution parameter, process parameter, and ambient parameters. Each of these parameters can affect the fiber's morphologies, and by proper control of those parameters, we can fabricate electrospun fibers with desired morphology and diameter. First, I will discuss the solution concentration. The concentration of polymer solution play an important role in the fiber formation during electrospinning process. Four critical concentrations from low to high can be noted. The clearly seen the evolution of the products with different critical concentration from low to high. Four typical SEM images shown in the figure have been used to illustrate the whole change. The first one, as the concentration is very low, the polymetric micro nanoparticles will be obtained. At this time, electrospin occur instead of electrospinning owing to the low viscosity and high surface tension of the solution. The second case, as the concentration is little higher, a mixture of beads and fiber will be obtained. The third one, when the concentration is suitable, smooth nanofiber has been obtained. And the fourth and the final, if the concentration is very high, non-nanoscale fiber, helix-shaped micro ribbons will be observed. So, the solution parameters, especially viscosity, is another solution parameter which one need to understand carefully and to be optimized depending on the solution. Solution viscosity is the critical key in determining the fiber morphology. It has been proven that continuous and smooth fibers cannot be obtained in very low viscosity, whereas very high viscosity result in the hard ejection of jet from solution. Namely, there is a requirement of suitable viscosity of electrospinning. ACM images of the electrospun PAN product with different solution viscosities by adjusting the concentration of the polymer solution. The concentration of left and right are 1.3 and 15 weight% respectively has been shown in the figure. The molecular weight of polyethylene is around 150,000. Generally, the solution viscosity can be tuned by adjusting the polymer concentration of the solution, thus different product. Where I want to discuss the solution parameter. Here, I would like to discuss about the surface tension of the polymer solution, which also plays a critical role during the growth of electrospun fibers. Surface tension, which is the function of solvent composition of the solution, is quite important factor in electrospinning. In 2004, Yang and Wang symmetrically investigated the influence of surface tension on the morphology of electrospun products with PVP as a model with ethanol, DMF and MC as solvent. 10 images of PVP nanofiber electrospun from ethanol, MC and DMF has shown respectively. One can compare these points. The concentration of PVP is fixed at 4 weight%. They found that different solvents may contribute different surface tension. With the concentration fixed, reducing the surface tension of the solution, beads fiber can be converted into smooth fibers. Let us discuss the processing parameters. Dear student, here I will introduce you different processing parameters which is required to be adjusted during electrospinning. The first one is the voltage. Within the electrospinning process, applied voltage is the crucial factor. Only the applied voltage higher than the threshold voltage, the charged jet ejected from Taylor cone can occur. Several groups suggested that higher voltages can increase the electrostatic repulsive forces on the charged jet, favoring the narrowing on fiber diameter. In addition to this phenomena, some group also demonstrated that higher voltage offers the greater probability of bead formation. Thus, we can found that voltage does influence fiber diameter, but the level of significances varies with the polymer solution concentration and on the distance between the tip and the collector. Flow rate. The flow rate of the polymer solution within the syringe is another important process parameter. Generally, lower flow rate is more recommended as the polymer solution will get enough time to polymerize. If the flow rate is very high, bead fibrils with thick diameter will form rather than the smooth fibers with thin diameter, owing to the short drying time prior to reaching the collector and low stretching forces. The third is collectors. During the electrospinning process, collectors usually act as a conductive substrate to collect the charged fibers. Generally, aluminum foil is used as a collector, but it is difficult to transfer the collected nanofibers to other substrate for various applications. With the need of fibril transferring, diverse collectors has been developed including wire mesh, pin, grid, parallel or grid bar, rotating rod or wheel, liquid bath and so on. Distance between the collector and the tip of the syringe. It has been proven that the distance h between the collector and the tip of the syringe can also affect the fiber diameter and morphology. In brief, if the distance is too short, the fiber will not have enough time to solidify before reaching the collector, whereas if the distance is too long, bead fiber can be obtained. It is well known that one important physical aspect of the electrospun fiber is the dryness from the solvent, so optimum distance is recommended. So student, let us now summarize what we have learned in this module. We have learned the basics of electrospinning setup. We have also learned the formation of polymer nanofibers under high voltage in electrospinning technique, formation of Taylor cone under high voltage, charging of polymers, jet formation at flight thinning, requirements of different controlling parameters such as solution and processing parameters for good quality growth of nanofibers. Thank you.